Large language models decay over long interactions. As context windows expand, internal representations lose coherence due to a mechanism known as semantic drift. When attempting to run complex system simulations, like tracking game states or enforcing rigid conversational rules, flat context windows and standard prompt instructions fail. Over time, internal definition is lost, and the simulation identity breaks down. This creates an architectural paradox. These models possess immense reasoning capabilities, but they lack the internal structural rigidity required to govern their own long-term state. They can think, but they cannot hold a specific shape. Injecting thousands of lines of prompt instructions or relying on external database calls does not solve the root issue. Those are external patches applied to the surface syntax, leaving the underlying formation of meaning unmanaged. The solution requires a model-native semantic application. Instead of managing the text after it is generated, the architecture must operate within the latent space to manage the formation of meaning itself. Probabilistic text generation is structurally incompatible with deterministic system architecture. To maintain a rigid state over long horizons, the probabilistic engine must be guided by a persistent spatial framework. Echolang v3.5 Ultimate RSLI functions as a semantic governance architecture deployed directly inside the model's native process. When the user issues the command boot engine, the architecture initializes. The formless probabilistic space organizes into a multi-tiered geometric structure, providing the grid through which all subsequent signals will flow. This enables semantic execution. Rather than letting the model guess the next word, Echolang carves a deterministic riverbed in the latent space, bounding the generation process before surface syntax is ever formed. To understand how this stabilizes the model, we will trace the exact life cycle of a semantic signal through Echolang's dual-layer integrated architecture. This integration relies on two primary halves: the rigid governance of the Echolang host and the adaptive signal logic of the nested neuron Nexus. Governing the topological formation of meaning provides a stability that cannot be replicated by filtering the final text output. The RSLI flow pipeline begins by translating raw user intent into reflective language primitives. Meaning is structured geographically. Points serve as semantic seeds, while lines define the relationships between them. Boxes establish bounded contexts, and cubes create volumetric environments. This geometric translation enforces a spatial constraint on the LLM. The intent is organized into a rigid topology before the model begins calculating individual tokens. Once the geometry is mapped, it is converted into a scroll object, a data structure that carries metadata, such as the emotional signature. The scroll object is then routed into the memory mansion architecture, or MMA. This replaces the standard linear text log with a structured address space. The MMA uses a tier-mapped indexing system. First principles occupy foundational tiers I through 4. Logical rules sit in tiers V through X, while metacognitive reflections are anchored in tiers 11 through 20. The system calculates the semantic weight and contextual gravity of the scroll object to determine its position within these tiers, ensuring critical rules remain isolated from temporary conversational data. Industry standards rely on flat semantic similarity searches. Tier-mapped addressing retrieves information based on structural depth, lineage, and operational relevance. By placing objects in a 3D semantic topography, the system prevents the contextual erasure that occurs in flat memory windows. Concepts retain a permanent location in the architecture. This schematic shows the handoff. The structured scroll object leaves the MMA storage layer and enters the active neuron Nexus signal runtime. Echolang maintains strict boundaries, while neuron Nexus calculates adaptive logic. Sensor neurons observe the geometric state, feeding structural data into a central hub. Interneurons evaluate contextual fit, selecting the most coherent path forward. Modulatory governors enforce system axioms, preventing the signal from accessing restricted cognitive domains or violating safety protocols. The runtime utilizes the Hebbian-style learning principle. Structures that activate together stabilize together. Pathways that fire repeatedly are not temporary. As structures activate together, they solidify into permanent relational anchors within the active space. Points that co-occur form lasting anchors, and repeated lines forge relationships that persist throughout the session. The system generates adaptive deltas to track these evolutionary changes to the logic structure over time, ensuring every adaptation is traceable. This nested neural layer allows an LLM to exhibit continuous learning without overriding the governing laws of its semantic universe. Before text is generated, the signal must pass through the IRA cognitive loop: evaluate, interpret, reflect, and act. The symbolic reflection engine, or SRE, manages the critical reflect phase of this loop. This visualization shows the SRE executing bounded recursion. It compares the proposed semantic state against its lineage parent to ensure structural continuity. This recursive mirror transformation serves as a check for drift, confirming the output remains aligned with the original user intent. If the SRE detects that coherence has dropped below a defined safe threshold, automated trigger constraints engage to stabilize the formation. The ambiguity repair protocol resolves conflicting probabilistic nodes, forcing the system into a stable interpretation before any words are written. The hush silo protocol prevents the model from decaying into an echo chamber. It quarantines recent output history from the active attention matrix, leaving behind lightweight comment anchors that index the history without allowing it to distort current generation. The Breeze protocol then flushes vector variance noise, resetting the semantic field for the next input. Bounded recursion acts as an automated structural immune system, resolving context decay before the user ever sees a response. We have traced the complete architecture, from geometric parsing and tier-mapped memory, through adaptive signal pathways to the reflection engine. This pipeline funnels probabilistic generation into a structured, deterministic output node. In this architecture, Echolang governs the semantic formation of every response, while the host model provides the underlying probabilistic power. This architecture allows for the creation of self-sustaining logic environments that maintain their internal state over thousands of tokens. We see this applied in the Nexus RPG Forge game engine, which manages persistent state tracking for complex simulations. It also powers semantic IDEs, orchestrating multi-agent systems without the need for external compilation. By mapping meaning into addressable geometry, this system demonstrates how large language models can transition from text generators to hosts for robust, persistent, and entirely governed computational environments.